Every story has a beginning, but the story of Earth, the vibrant world we call home, doesn't begin with Earth itself. Its genesis reaches back 13.8 billion years ago. Within the first 3 minutes, as the universe remained incredibly hot and dense, protons and neutrons fused, forging the nuclei of the lightest elements, hydrogen and helium, the building blocks of everything to come. Within the first 3 minutes, as the universe remained incredibly hot and dense, protons and neutrons fused, forging the nuclei of the lightest elements, hydrogen and helium, the building blocks of everything to come. Eventually, at the heart of the densest gas clumps, pressure and temperature soared to a critical point. Nuclear fusion ignited. Hydrogen began fusing into helium, unleashing immense energy as light and heat. The very first stars were born, ending the cosmic dark ages. These stellar giants didn't stand alone. They clustered into the first galaxies, laying the groundwork for the large-scale structures we marvel at in the universe today. But these first stars were just the beginning. Their lives and their explosive deaths would forge the heavy elements necessary for the next pivotal chapter in our story. Our solar system's collapse from this molecular cloud was likely triggered by the shockwave from a nearby supernova. While the sun ignited at the center, the remaining swirling disk became the birthplace of the planets. The intense heat from our newborn sun created a crucial boundary in the protoplanetary disk, the frost line. Inside this line, closer to the sun, temperatures were too high for volatile compounds like water, methane, and ammonia to freeze. So here, the primary building blocks were rocky and metallic dust particles, and so our Earth was born. But this infant world was a far cry from the serene blue marble we know. It was a crucible of fire, chaos, and a cataclysmic event that would shape its destiny forever. The newly formed Earth was utterly alien to us. This was a world of fire and brimstone, an epoch named after the Greek god of the underworld, the Hadean Aeon, lasting from roughly 4.5 to 4.0 billion years ago. Earth's primordial surface was a churning magma ocean, kept molten by 3 relentless energy sources: residual heat from its formation, a heavy and continuous bombardment from lingering asteroids and meteorites known as the Late Heavy Bombardment, and the decay of short-lived radioactive elements within its core. The early atmosphere was incredibly thick and toxic, dominated by colossal amounts of carbon dioxide, potentially 54 times pre-industrial levels, along with water vapor, hydrogen, and other volcanic gases. Oxygen was virtually absent. Surface temperatures likely averaged 75 degrees Celsius, but under immense atmospheric pressure, it was an unimaginable cauldron. It was during this cataclysmic era that one of the most profound events in Earth's history occurred. The prevailing theory for the Moon's formation is the giant impact hypothesis. It proposes that around 4.5 billion years ago, a Mars-sized protoplanet scientists call Theia slammed into our proto-Earth at incredible speed. The collision was so violent, it nearly tore both planets apart. Theia's iron core likely sank to merge with Earth's core, adding to our planet's mass and density. Simultaneously, a vast amount of molten rock debris from the mantles of both Earth and Theia was flung into orbit around our battered planet. Within a remarkably short time, perhaps a few hundred to a few thousand years, this superheated debris coalesced under gravity, forming our moon. This wasn't merely a collateral event, it was a pivotal moment that defined Earth's characteristics forever. The resulting moon, massive for a satellite, generated gravitational forces that stabilized Earth's axial tilt, providing a stable climate conducive to complex life's long-term evolution. Moreover, the impact may have stripped away Earth's thick primordial atmosphere and potentially delivered crucial volatiles like water. As the inferno of the Hadean Eon faded, Earth entered the Archean Eon, spanning from 4.0 to 2.5 billion years ago. This was a blue planet of vast oceans and only small, emerging continents. The atmosphere remained oxygen-free, instead rich in carbon dioxide, methane, and ammonia. The stage was now perfectly set for the most astonishing act of all, the transition from inert matter to living organisms. The Archean oceans were a primordial soup, teeming with a diverse array of dissolved chemicals. The energy required for chemical reactions was abundant. Intense ultraviolet radiation from the sun, as there was no protective ozone layer yet, relentless thunderstorms and lightning, and the scorching heat spewing from undersea hydrothermal vents. These conditions were ideally suited for the synthesis of complex organic molecules from simpler inorganic ones. One of the greatest puzzles of life's origin was the chicken or egg question. Which came first, DNA or proteins? DNA stores genetic information, but needs proteins, enzymes, to replicate. Proteins perform cellular functions, but need DNA's code to be built. The RNA world hypothesis offered an elegant solution. RNA, a molecule similar to DNA, has a unique ability. It can both store genetic information and catalyze chemical reactions as ribozymes. It's plausible that the earliest life forms were based on self-replicating RNA molecules, before evolving into the more stable and complex DNA protein system we see today. The earliest life on Earth was simple, single-celled prokaryotes, cells without a nucleus, possibly appearing as early as 3.8 to 4.1 billion years ago. The oldest and clearest fossil evidence we have are stromatolites, layered rock structures dating back 3.5 billion years. Stromatolites aren't fossils of a single organism, but petrified cities built by colonies of bacteria, particularly cyanobacteria or blue-green algae. These cyanobacteria secreted sticky mats that trapped sediment in shallow waters. Over time, these sediments solidified, while the bacteria grew upwards towards the sunlight, creating new layers over old ones, forming the dome-like structures we see. For over a billion years, this seemingly innocuous waste product silently built up, until the waste became a weapon and the slow trickle of oxygen turned into a devastating flood, fundamentally reshaping our world and setting the stage for all complex life to follow. The oxygen revolution, a planetary transformation. For over a billion years, cyanobacteria in the oceans relentlessly produced oxygen. But this world-altering gas didn't immediately appear in the atmosphere. It was locked away in the oceans until a monumental turning point, the Great Oxidation Event. Initially, any oxygen produced immediately reacted with dissolved iron in the seawater, causing a planetary-scale rusting. The insoluble iron oxides settled to the ocean floor, accumulating into vast, layered geological structures known as banded iron formations, Earth's most significant source of iron ore today. Additionally, oxygen reacted with volcanic gases like methane. The early oceans and atmosphere acted as a vast sink, absorbing the oxygen. For most life on Earth at that time, anaerobic organisms that had evolved in an oxygen-free world, the appearance of this gas was catastrophic. Oxygen is a highly reactive gas, toxic to their biochemistry. The GOE triggered one of the earliest and perhaps most severe mass extinctions in Earth's history. Vast numbers of anaerobic organisms perished, with only those able to hide in oxygen-free environments, like deep-sea mud, surviving. Earth was being purified by the very waste products its life had created. The effects weren't just biological. The rising atmospheric oxygen reacted with methane, a powerful greenhouse gas, converting it into far weaker carbon dioxide. This dramatic drop in greenhouse warming caused Earth to cool drastically, likely triggering one of the longest and most severe ice ages, the Huronian glaciation. Second, the ozone layer. In the upper atmosphere, solar ultraviolet radiation reacted with oxygen molecules, breaking them apart and reforming them as ozone. This nascent ozone layer became a vital shield, absorbing most of the harmful UV radiation from reaching Earth's surface. This protection was absolutely crucial for life to eventually colonize land. And so, the greatest pollution event in Earth's history, born from the waste products of bacteria, became the indispensable catalyst for the evolution of all complex life, including us. We all breathe the toxic waste of our microbial ancestors, using it as the very energy that sustains our lives. This dramatic transformation solidified Earth's destiny as a living, breathing planet, ready for the next astonishing chapters of evolution.